A large outcropping on the coast of Lake Champlain, Lone Rock Point is home to some of the hardest climbing in Vermont. Closed to climbers until very recently, this area provides scenic views, interesting routes, and difficult climbing. In this video, we will talk about the structure of these rock formations, as well as the chemistry behind them. Consisting of a large dolostone roof perched on top of a bed of shale, the climbing here is sometimes inaccessible in the spring. As runoff increases after winter, the water level of Lake Champlain rises. This rise then causes the lower layer of shale to wear away, leaving behind a small cave in the main area of the crag.
This shale breaks easily into thin pieces. It is primarily made out of many clay minerals, such as chlorite, kaolinite, illite, and montmorillonite, as well as other phyllosilicates. Phyllosilicates are minerals that are made up of sheets of silica, oxygen tetrahedra. Each tetrahedra has one silicon cation in coordination with 4 oxygen anions. In phyllosilicate minerals, each tetrahedra shares 3 of these oxygen atoms with its neighbors. These tetrahedral sheets are then associated with octahedral hydroxide layers, where a cation, commonly magnesium or iron, is in coordination with 6 hydroxide ions. This can be arranged in one of several ways.
For example, in kaolinite, the simplest clay mineral, each unit layer consists of only one tetrahedral and octahedral sheet, known as a TO structure. In micas, each unit layer consists of a tetrahedra, octahedra, tetrahedra, or TOT sandwich, some coordinating cations, and another TOT layer.
The atoms and molecules in each unit layer are held together with mostly covalent and a few ionic bonds. These bonds are strong, so each unit layer does not break apart easily. However, the unit layers are held together with weak van der Waals interactions. Thus, these layers break apart easily along parallel planes, as seen in the shale here.
Because this shale wears away so easily, a small cave remains underneath the main area of the crag, perfect for a nap or just staying out of the wind. Dolostone is a very interesting rock to climb on, as it tends to be very crumbly. This is usually referred to as being chossy. This leaves the base of the wall littered with hand-to-fridge-sized debris. On the wall, this means that the roots can be constantly changing, especially after the freeze-thaw cycle of winter. Route by route, the holds are generally hard to find and roots can be difficult to ascend or climb without falling on the first attempt.
This is because dolostone is primarily made of dolomite, which is a carbonate mineral with the formula CaMgCO32. Dolomite has a rhombohedral crystal structure, where carbonate ions are in coordination with calcium and magnesium ions.
Carbonate minerals, like dolomite, are susceptible to dissolution by slightly acidic rain. In the atmosphere, water vapor combines with various oxides such as carbon dioxide, sulfur dioxide, and nitrous oxides to form acids such as carbonic acid, sulfuric acid, and nitric acid. These then react with the dolomite to dissolve it in mechanisms similar to the following double replacement reaction. One formula unit of dolomite reacts with 4 molecules of a monoprotic acid to form ions of a soluble salt, carbon dioxide gas, and water.
However, dolomite has a 1-to-1 ratio of calcium and magnesium ions, meaning that it is in the middle of a solid solution between pure calcite and pure magnesite. A solid solution is a mix of 2 crystalline solids. These 2 diagrams show the mixing ratios of the calcium, magnesium, and sodium end members. Dolomite is anything in the pink sections. Because it is in the middle of a solid solution series, it is more resistant to acid dissolution. As a result, the acid can only make progress at dissolving it where there are more faces to attack the rock from, such as where there are cracks. By dissolving these cracks, it breaks the dolostone into the blocky structure that we see here and makes it chalky.
One of the most striking features of Lone Rock Point is the interesting colors of the rock, which you notice almost immediately as you arrive at the crag. In the large overhanging section to the right of the crag, the rock is a striking yellow-orange color, evoking thoughts of climbing in Spain. As the rock becomes more low angle, it starts to darken and become less crumbly. The best example of this is the direct center of the crag, where the walls are nearly featureless. This makes them much harder to climb, and there are only a couple routes up this section.
This color comes from the oxidation of iron. In the crystal structure of dolomite, divalent or 2+ iron can easily replace a divalent magnesium due to their similar size and charge. When this iron gets introduced to oxygen, it gets easily oxidized, turning from ferrous iron 2+ to ferric iron 3+. This turns it orangey red, the color of rust, as seen on these dolostone cliffs.
Geochemical concepts like acid dissolution and silicate structure weaknesses are essential to our daily lives. When climbers know how the rock will behave, it is much easier to plan their day and their route. For example, at this dolostone cliff, by knowing beforehand that it's crumbly, one can know to watch out for loose holds, make sure they bring a helmet for safety, and also bring a stick clip to pre-clip the carabiners and prevent a ground fall. For everyone else, these concepts inform geologists and city planners so that your house will not fall off a cliff.